Vectors and scalars. Before working through this video, you will need to know basic concepts about vectors. If necessary, you should refer to the following video which covers this topic. Thanks for watching this video and don't forget to like, subscribe to the channel and activate the notifications. It's very important to the continuity of this channel. The physical quantities that are used to describe the motion of objects can be divided into two categories, scalars and vectors. Scalars are quantities that are fully described by a magnitude or numerical value alone. Vectors are quantities that are fully described by both a magnitude and a direction. The table alongside lists some examples of scalar and vector quantities. A vector quantity is represented by a line with an arrow. The direction the arrow points represents the direction of the vector. The length of the line represents the magnitude of the vector to a chosen scale. Graphically, vectors are drawn as arrows because an arrow has both a magnitude and a direction. Numerous notations are commonly used to denote vectors. In this channel, vectors will be denoted by an arrow above the letter or as italic bold type. Look at the examples. Vector addition. When two or more vectors are added together, their combined effect is known as the resulting of the vectors. When adding vectors, we take into account their direction. Two vectors are added by placing the tail of one to the tip of the first, placing the arrowhead of one to the tail of the other. This method of adding is called the tail-to-head method. It's very useful to represent vectors on a Cartesian plane because in this way is clearer the direction and the scale chosen. Let us consider three examples of vector addition. Let's add the vectors b and d. Draw a line to represent the first vector, vector b in this case. Draw a line to represent the vector d, starting at the end of the vector b. In other words, draw the vector d with its tail at the head of vector b. The vector sum, or resulting vector, is the vector that extends from the tail of b to the head of d. The vector b measures 4 units on the right, and the vector d measures 5 units on the right. So, the resulting vector measures 9 units on the right. Let's add the vectors d and c. Draw a line to represent the first vector, vector d in this case. Draw a line to represent the vector c. Draw the vector c with its tail at the head of vector d. The vector sum or resultant vector is the vector that extends from the tail of d to the head of c. The vector b measures 5 units on the right and the vector c measures 3 units on the left. So the resultant vector measures 2 units on the right. Let's add the vectors a and b. Draw a line to represent the first vector, vector a in this case. Draw a line to represent the vector b. Draw the vector b with its tail at the head of vector a. The vector sum or resultant vector is the vector that extends from the tail of vector a to the head of vector b. As we can see, when two perpendicular vectors are added, we get a right triangle, and the resultant vector is the hypotenuse. So the Pythagorean theorem can be used to calculate the resultant vector. The magnitude of a vector is shown by two vertical bars on either side of the vector, or we write the vector with no bolt. We can summarize the addition of vectors as follows. If two vectors are in the same direction, they are added as if they were numbers. If two vectors are in the opposite direction, they are subtracted as if they were numbers. If two vectors are in perpendicular directions, they are added using the Pythagorean theorem. At last but not least, we will see how to subtract two vectors. Subtracting one vector from another is very simple. We just reverse the direction of the vector to be subtracted and add this to the other vector. Let's find the difference between the vector D and the vector B. Draw the vector D, then draw the vector B with its tail at the head of vector D. Resultant vector is the vector that extends from the tail of vector D to the head of vector B. A bear walks 3 kilometers to the north and then 4 kilometers to the east. Calculate the total distance traveled. In the first part of his journey, he traveled 3 kilometers, and in the second part, he traveled 4 kilometers. This gives us a total distance traveled of 3 plus 4 equals 7 kilometers. Calculate the displacement. The bear's resultant displacement is the vector from where he started to where he ended. It is the sum of his two separate displacements. We use the tail-to-head method to find this vector. Now we use the Pythagorean theorem. In the end, the bear is 5 kilometers from the starting point. A river flows from west to east with velocity of 1 meter per second. A boat leaves the south bank heading due north at 2.5 meters per second. Find the resultant velocity of the boat. The boat is attempting to cross a river. It wants to cross directly to the opposite bank, but the current moves the boat sideways at the same time as the boat is forwards. The boat does not move in the direction in which it is pointed. The outcome is that the boat moves diagonally relative to the shore. The reason is that the river carries the boat downstream. In effect, we have two velocities. The velocity due to the boat crossing, which is directed straight across the river. The velocity due to the current, which is directed downstream, at right angles to the boat velocity. These combine to give a resultant velocity, which will be diagonally downstream. Its total velocity relative to the shore is the sum of its velocity relative to the river plus the velocity of the river relative to the shore. In order to find the resultant velocity, we will use the tail-to-head method. Pay attention. An aircraft is flying due north with a velocity of 720 km per hour. A side wind of velocity 76 km per hour is blowing due east. What is the aircraft's resultant velocity? The wind moves the aircraft sideways at the same time as the aircraft is heading north. The outcome is that the aircraft moves diagonally relative to the ground. The aircraft does not move relative to the ground in the direction it points. Rather, It moves in the direction of its resultant velocity. In order to find the resultant velocity, we will use the tail-to-head method, as we did in the previous example. Pay attention. Now let's see how to add vector quantities that are not at right angles. An aircraft flies 300 kilometers due east and then 500 kilometers northeast, as shown below. Calculate the final displacement of the aircraft. We will use the tail-to-head method, as we did before. We want to calculate the magnitude of the displacement, but here the two displacements are not at 90 degrees to one another, so we cannot use Pythagorean theorem. In situations like this, the law of cosines can be used to calculate the magnitude of the resultant vector. If necessary, you should refer to the following video, which covers this topic. Looking at the figure, we see the angle theta plus 45 degrees is 180 degrees. Then theta equals 135 degrees. The angle opposite to the resultant vector is theta. Take the law of cosines and perform the calculations. The law of sines can be used to calculate the direction alpha of the displacement. Take the law of sines and perform the calculations. So the displacement is 601.08 kilometers at an angle of 36.2 degrees northwest.